Good evening, everyone, and welcome to today's Cheenta student research presentation. We are extremely proud to showcase another outstanding work from the Cheenta AI Research Lab. Today's presentation is titled Using Interpretable AI to Understand How Deep Learning Models Function, a topic that sits right at the intersection of machine learning, time series analysis, and explainable AI. Our presenters are Kanishk Sharma, Aditya Nanda, and Aditya Saif. With that introduction, I invite Kanishk, Aditya, and Aditya to begin their presentation.
Yeah, so I'll be giving you the introduction and the literature review. Next slide. Yeah, next slide. So, how did we get to our problem statement? Cryptocurrencies like Bitcoin are very volatile because they're driven by technology shifts, regulations, and investor sentiment, making the very like when short-term trends very hard to predict and very valuable as they could return many profits. So learning models show strong forecasting ability, but their black box nature limits transparency and trust in financial decision making. So we cannot trust deep learning models. So that's proves us to the problem statement of this paper. Understanding feature importance and how it affects a model decision making in predicting cryptocurrency prices using deep learning and interpretable AI tools. Next, miss. So the related works are the normal econometric models, which have used ARIMA and GARCH for volatility and linear trend modeling. And then there are the classical machine learnings, which people have applied SVM, Randall Forest, and XGBoost. And the deep learning approaches are also there, which use models such as LSTM and CNN LSTM. And few works also use transformers and explainability using techniques like SHAP and line for interpretability. So our work develops a complete DNN pipeline, which is a deep neural network pipeline, designed specifically for the cryptocurrency domain, with our main goal on interpretability rather than predictive nature. Basically, understanding how and why the deep learning models make decisions in these highly volatile markets, rather than just improving our performance score. So we've used two architectures, the CNN by LSTM and transformers, uh, which are analyzed using our interpretability toolkit, which includes SHAP, integrated gradients, and attention visualization. This framework reveals which indicators and temporal patterns meaningfully drive model predictions, contributing insights valuable for traders, researchers, and explainable AI finance applications. Um, our study focuses on Bitcoin to USD exchange rates. Uh, Kanish can take over from here.
So I will be explaining the model architecture of our paper. For our study, we have used Bitcoin as the primary asset. The retrieval of the data is done through Y-Finance, which is an API supported by Google Colab, on which all our experiments were conducted. The data spans from January 1st, 2018 to the most recent available data, so almost about 7 years. The retrieved data consists of multi-index OHLCV features, namely open, high, low, and close prices for a particular day, and the volume of the asset traded. Once this is done, we clean the data by removing entries with missing values and duplicate timestamps. Finally, the clean data is then split into 80% training and 20% testing data with no overlap to ensure no data leakage. Can we go to the next slide? Okay, so once the data is clean, we now engineer our feature set. in which each feature contributes information on trend, volatility, momentum, and market strength. The engineered features belong to two broad categories: technical and regime indicators. The closed price series is transformed into multi horizon log returns, short and medium simple moving averages and weighted moving averages, rolling volatility, realized volatility, oscillators such as RSI, MACD, CCI, Williams R percentage, accumulation distribution line, skewness, and regime flags based on volatility and long term moving averages. All these indicators are concatenated at each timestamp into a 24-dimensional feature vector, and each column is standardized with a Z-score transform. Now we sequence the entire time series data so that our deep sequence models can actually understand them. So we develop overlapping windows of size 30, and for each timestamp you have a 24 feature vector. So finally we get a sequence of 30 cross 24 dimensional tensors that can be provided as inputs to the model. Now can you go to the next slide? So this is the data flow diagram of our proposed pipeline. Next slide. Right. So now since we are doing a price prediction, it is necessary to assign labels to each tensor, which brings us to our labeling algorithm, which is a combination of volatility based labeling and a zigzag trend filter. It's a two-step process, not that difficult. A three-class regime label is constructed for each timestamp. We compute a 10-step forward return and compare it with a volatility adjusted threshold. If there's a large positive movement, then uptrend, that is y equal to 0, is assigned. If there's a large movement, large negative movement, then downtrend, which is y equal to 2, is assigned. And if there's small movement, then it's assigned as sideways, which is y equal to 1. In parallel, pivot-based zigzag thresholds on price changes define a structural label over swings between pivots with a threshold of 3%. If there is, so finally, what the algorithm does is, if there is a large movement, that is, if y is equal to either 0 or 2, then the volatility label is used, and in case of sideways, the zigzag label is used. Moreover, a minimum regime length constraint then merges any run shorter than 5 timestamps into neighbors to avoid very short or noisy labels. So finally, each tensor is assigned a label, and then this sequence is provided as input to the deep learning models. Can we go to the next slide? Right. So the first model that we use is a hybrid bi-LSTM. This architecture chains convolution, bidirectional recurrence, and attention to mix short and long horizon information in a way that is also easy to interpret. The first layer is a 1D convolution with 32 filters and kernel size 3 that slides over time, followed by a ReLU nonlinearity. This block captures short range temporal patterns such as local shocks or micro trends across multiple indicators, and it also reduces noise by aggregating over neighboring timestamps. Then max pooling with pool size of 2 downsamples the time axis and focuses on the strongest local activations, while dropout regularizes the convolution representation. Together, they reduce sequence length, improve computational efficiency, and help the model generalize to unseen regimes. The downsampled sequence goes through a bidirectional LSTM that outputs a hidden state at each pool timestamp. The forward and backward passes encode past and future within the window context, allowing the model to capture medium range dependencies and, and pattern ordering within the 30-step history. An additive attention mechanism learns a scalar score for each hidden state, normalizes it into weights, and forms a weighted sum context vector Z. This focuses this focuses the model on the most informative timestamps, example regime transitions or volatility spikes, and the attention weights are directly interpretable as temporal importance scores. The context vector then passes through a fully connected layer with 64 ReLU units and dropout of 0.3 to form a compact nonlinear representation before classification. This layer mixes information coming from different times and features, while dropout further reduces overfitting. A final linear layer and three-way softmax maps the representations to probabilities over downtrend, sideways, and uptrend regimes. This produces calibrated class scores and can be used for both decisions and interpretability analysis. Now, for this model, what is our optimization setup? We use a batch size of 256 with 200 epochs each, and it is trained with the Adams optimizer with a learning rate of 5 into 10 to the power minus 4. The loss function is which is used is class weighted sparse categorical cross entropy. We also use a learning rate scheduler. uh, what that does is, if there's a constant stagnance in each epoch, uh, no, what it does is, if there is a constant stagnance in each epoch loss, then the learning rate is reduced, and then the model continues to train it so that there is no loss of information or there's no data leakage. Class weights then mitigate imbalance between regimes, and the trading schedule stabilizes learning across different market conditions. This is the CNN BioLSTM attention model. The next slide shows architectural diagram for the same. Now we can go to the next slide. The next slide brings us to our second deep learning model, that is a transformer based model. This architecture replaces recurrence that was used in BioLSTM with self attention, which directly models all pairwise time step interactions and provides richer temporal credit assignment. Each time step vector in X, which is our tensor, is linearly projected into a 64-dimensional embedding, and sinusoidal positional encoding are added. The projection learns a feature embedding space, which positional encodings inject timestamp order, which is otherwise lost in pure attention. The embedded sequence is regularized with dropout and normalized, stabilizing gradients and improving optimization. This is important because self-attention blocks can otherwise become numerically unstable on long and noisy sequences. Then we have two stacked encoder blocks. Each block consists of the following: a multi-head self-attention, which consists of 4 heads, in which queries, keys, and values are computed from the same input, and attention weights, softmax, mix information across all time steps. Multiple heads let the model attend to different temporal patterns. For example, very recent bars versus older pivots, or simultaneously capturing long range dependencies that LSTMs might struggle with. The attention output is added back to the input and normalized. This preserves original information and eases training of deeper stacks. A two-layer MLP with 128 hidden units and dropout of 0.3 is applied independently at each time step. This enhances the expressiveness of per time step representation after attention has mixed temporal context. We also add another residual and normalized layer to this that stabilizes the transformation and helps gradients flow through multiple blocks. After the final encoder block, the sequence of time step representations is averaged along the temporal axis to obtain a single vector z. This operation aggregates information from all time steps with attention having already weighted which parts of the history are most influential. Now, after these two encoder blocks end, we have the z vector is fed into a 64 unit ReLU dense layer with a dropout of 0.3. This compresses and refines the global sequence representation before classification, similar to the BioLSTM model. A final dense layer and a three-way softmax, just like how we did in BioLSTM, produces probabilities for the three regimes trained with the same loss and optimization schedule as the bilastium. The self-attention matrices, especially from the first time step, the self-attention matrices, especially from the first encoder layer, provide a direct view of how much each time step attends to every other. Averaging attention across heads yield heat maps that show whether the model emphasizes recent bars, earlier regime shifts, or specific volatility events when making predictions. As mentioned above, optimization setup is same as the hybrid bilastium model. Now the next slide shows you the architectural diagram of the transformer based model. Now we can move on to the next slide, which shows us the baseline models that we have considered for comparison. We have considered certain classical machine learning baseline models for comparison. The objective is to benchmark the deep learning models against these baseline learners on flattening features. The baseline models include random forest with 200 trees and the max depth of 10, XGBoost with 200 boosting rounds and max depth of 6, and support vector machine with RBF kernel and C equal to 1. For these model, each 30 cross 24 tensor is flattened into a 720 dimensional vector and used to train on a subset of 2000 training and evaluation on 500 test sequence. They are evaluated on accuracy and weighted F1 score to handle class imbalance. We can go to the next slide. So once the models complete processing the data and coming to conclusions, we definitely need to understand why these conclusions or decisions are being made. That brings us to the most important part of the paper, and that is the interpretability of the models. The interpretability techniques that we have used are SHAP values that measure global feature importance for deep models using gradients, and they reveal which features have the most influence across the samples. The second technique that we have used is integrated gradients. These provide sample specific attributions, highlight which feature drive the individual predictions in deep models. Then we have attention visualization. For transformer encoders, self-attention weights indicate which time step for which indicates which time step the model focuses on, highlighting temporal dependencies. Then we have the surrogate modeling, which fit a simple model. For example, we have used the logistic regression to mimic deep model predictions. Coefficients give feature importance in model agnostic way. And finally, the last interpretability technique that we have used is permutation importance, which is used for the classical machine learning models to measure performance drops when a feature is shuffled. Larger drops indicate more important features. So combining these techniques ensures robust interpretability, confirming that models rely on meaningful temporal and feature informative rather than artifacts. So that completes the model architecture. Now I'll hand it over to Aditya, who is going to explain the results of our paper.
So now I'm going to tell the results of the paper we got. So we compared the models on two main categories, which are accuracy and F1 score. So as you can see, the CNN bilastium model performed best on accuracy, while the transformer achieves the best F1 score because of its balanced handling of all the classes. And classical models perform significantly worse, especially SVM, which is support vector machine, and random forest. Next slide. So for the CNN BioLSTM, the SHAP analysis shows that volatility and multi-day returns carry the strongest influence on its decision making. And the volume-based indicators and the moving averages also contribute. However, the integrated gradients highlight smoothened trend indicators like simple moving averages and MACD components and rolling volatility as the key drivers for the model. And so overall, this model behaves in a way that aligns closely with traditional technical analysis. Next slide, please. So for the transformer model, SHAP ranks regime change indicators and weighted moving averages as the most influential. And the secondary contributors include short-term returns, volatility, and the accumulation distribution line. So integrated gradients further highlight smoothing trends and volatility features, showing that the transformer relies less on raw returns and more on stable regime signals. Next slide. So the transformer's attention maps reveal which time steps the model focuses on while making the predictions. So the usually, as you can see, the attention is strongest on the most recent time steps, but during big regime changes, the model shifts focus to earlier points. So next slide, please. So coming to the classical machine learning versus the deep learning models. So we found that the classical models like XGBoost and random forest rely on simple features and they lack the ability to capture the time dependent relationships. And their explanations are also very shallow and unstable. So as I said, the deep models benefit from sharp integrated gradients and attention heat maps, making them more useful for interpretability. Next slide, please. So yeah, as I had mentioned, the CNN bialystium relies more on raw returns, short-term momentum, and basic trend indicators. And the transformer focuses more on smoothened indicators and volatility signals. And also, its attention mechanism gives it a deeper temporal awareness, especially during volatile or shifting regimes. Hence telling us why its F1 score was the highest. Next slide, please. So, in conclusion, what our paper basically found out was that the hybrid BLSTM and transformer models they have valuable but different interpretability strengths, and so practitioners should be very careful in what context are they using the models, because the hybrid BLSTM model provides straightforward and finance aligned explanations, which is similar to what traders and practitioners do. However, the transformer offers richer and more adaptive temporal reasoning through its self-attention, which is helpful in multi-regime, highly volatile environments like cryptocurrency. So the future works that explore this topic may also include heavier ensemble architectures. They can all expand to multi-cryptocurrency datasets, like include other cryptocurrencies like Ethereum or Litecoin, for example. And they can also study cross-asset correlations to extend the interpretability further to broader financial systems. Next slide. So that is the main our main paper, and these are the references we have used throughout the paper.
Okay, that's really great. So now, like, if you have any question, feel free to put it in the comment section. We will be really happy to answer your questions. And thank you so much, Kanish, Aditya, and Aditya, for joining this session. Thank you so much.
Thank you.
Thank you.
Thank you.